Chemistry, the Central Science, Chapter 3, Chemical Reactions and Reaction Stoichiometry, Lesson 2. So we use the value of a mole to represent a large number of atoms. So this is, or molecules or whatever, particles, whatever it is that we're interested in. So a mole is a counting number, and there are a lot of said particles in one mole of a number. So Avogadro's number, which is how many particles there are in one mole, is 6.0221415 times 10 to the 23rd. We will just use 6.022 times 10 to the 23rd. We don't need that many significant figures. So 1 mole of anything represents 6.022 times 10 to the 23rd of that particular substance. It works the same way as a dozen would. Does not matter what you are saying. I have a dozen shoes, a dozen donuts, a dozen eggs. It's always representing the number 12. Just like if you have a pair of socks or a pair of shoes or a pair of cats, pair means 2. So it's a number. It is a counting number. If you have a mole of anything, it is always 6.022 times 10 to the 23rd of that substance. So we can use moles to figure out the molar mass of a substance. And so that is going to be what that substance mass is in grams if you have 1 mole of it. So our unit is grams per mole. And we'll look at the different conversions that we can do. Down here, this is representing a mole of each of these elements. So I think that's copper there. This might be graphite, which is carbon, one of the allotropes of carbon. This is sulfur. Here we have some mercury, and then we have some iron nails. So this is all representing a mole. Regardless of whatever it is that you're talking about, if you have a mole of carbon or a mole of iron or a mole of sulfur, it all means that you have the same quantity of those particular atoms. They might weigh differently, which we know they do because we look at the periodic table. So how does this conversion work exactly? Well, when we talked about atomic mass units, we used the carbon-12 isotope. So carbon-12 because 99% of all the carbon atoms that exist in the universe are carbon-12. So we say that it weighs exactly 12.00 AMUs. We then know that if we have 1 mole of carbon atoms, which is 6.022 times 10 to the 23rd, by looking at the periodic table or assuming that it is exactly equal to 12.00 grams, we then see that the mass of 1 AMU is equivalent to 1.66 times 10 to the negative 24th grams. So if this is our equivalency, and we see that atoms can cancel out, we then know that 1 AMU is 1.66 times 10 to the negative 24th grams, or if we divide 1 by 1.66 times 10 to the negative 24th, we get 1 gram equals 6.022 times 10 to the 23rd AMUs. So 1 gram equals 1 mole of atomic mass units. So when we represent molar mass, we give it a big capital letter M, and it is grams per mole. And we also recognize that Avogadro's number comes up in that, and assuming that if we have 1 mole of a substance, we have 6.022 times 10 to the 23rd atoms or molecules of that particular substance. So when we want to do some conversions, molar mass is what we need to have if we're going to interconvert between mass and moles. So mass to moles or moles to mass, we have to have a molar mass, which makes sense because it says moles and mass in the conversion. So going from the mass of a substance, let's say I'm given 100 grams. Well, then I look at what I'm interested in, find the molar mass on the periodic table by looking at the atomic weight, putting that in units of grams per moles. If we divide our mass by our molar mass, we get to moles. Vice versa, if we're given a number of moles, we simply multiply by the molar mass, and that will give us a specific number of grams. When we want to know how many atoms or molecules, particles, formula units, electrons, however many we're looking at, we use Avogadro's constant to convert between moles and what we're interested in. So if we're given moles, we multiply by Avogadro's number to get to the particles that we're interested in. And we will expect to have a fairly large number here. So times 10 to the something represents our particles. If we are given some number of particles, we divide by Avogadro's number to get back to moles. There is no direct conversion between grams and particles. You always have to stop off here in the land of moles. So grams to moles, we divide by the molar mass. Moles to grams, we multiply by molar mass. Moles to atoms, we multiply by Avogadro's number. Atoms to moles, we divide by Avogadro's number. So when you have a number of moles, it should not be times 10 to the 20th moles. You might have, I don't know, times 10 to the third. You could have 1,000 moles. That's reasonable. You can also have masses that are kilograms, and that's reasonable. So you want to think about what it is, what numbers you should expect to get. So once again, how do we find the molar mass? Well, for any molecule, the molecular mass, looking at one particular unit, or the formula mass, is measured in AMUs. That is the same number when we look at 1 mole of substance and we put that into grams. So we saw previously that a molecule of sulfur dioxide weighs 64.07 atomic mass units. If we have 1 mole of sulfur dioxide, now it weighs 64.07 grams. So the formula weight is not the same as a molar mass, right? Formula weight is looking at the atomic level. What is the same is the number. So the numbers are the same, but the units are different. So some conversion practice. How many calcium atoms are in 30.00 moles of calcium? How many grams of calcium are present? So I always start with my given information and I set up my picket fence. So I start with 30.00 moles of calcium because I want to find atoms. I know that if I have a mole of calcium here, it has to go on the bottom here, so it will cancel. My conversion factor is 1 mole of anything is 6.022 times 10 to the 23rd. So I multiply, I pay attention to significant figures. There are 4 in what I start with, so there are 4 in what I end with. This just tells me how many zeros I have to move, right? How many places past the decimal point I have to move this. This has nothing to do with the number of significant figures. This just tells me where my decimal point is. So how many grams is this? Well, once again, I have to start with my moles. Moles to grams means I multiply by the molar mass. So I look at the periodic table and see that the number under calcium is 40.08. I label that grams because it's grams per mole. Moles are here. 1 mole is here. Multiply, sig figs, 1,202 grams of calcium is the same as 30 moles, which is the same as having 1.807 times 10 to the 25th atoms of calcium. Anytime you are doing any of these conversions, it's always going to be 1 mole, no matter what, within the conversion factors. So how many moles of nickel are there in 5.00 times 10 to the 21 atoms of nickel? Given information, I write that down first. I see atoms are here, which means atoms go on the bottom. It is a large number of atoms that are in 1 mole. So I'm dividing by Avogadro's number. So this number divided by this number gives me 8.30 times 10 to the -3rd moles of nickel. Notice Avogadro's number, comparing it here, right? There's a difference of times 10 to the 2. So I have 100 times less, at least, the number of nickel atoms, which makes sense then why I have a small number here. If you have a number that is 10 to the 23rd or bigger, you expect to have more than a mole. If it's 10 to the 23rd smaller, right, than 6.022, you are going to have less than a mole. How many moles are present in 47.8 grams of scandium? Well, I'm given mass. I want to find moles. So my relationship then is, what is the molar mass? I look at the periodic table. The number under scandium is 44.96. So that is attached to my grams. Grams are here. I have to be able to cancel. So I'm dividing by the molar mass to show that I have 1.06 moles of scandium. And comparing my mass that I'm given to the molar mass, I have more than a mole. So this number makes sense, but not by much, right? A little over 2 grams more. How many atoms of carbon are in 619 grams of C12H22O11, which is a molecule, or not a molecule, but the compound of sucrose, table sugar? So this is going to be one step further because now we're looking at the individual atoms that are present. So I know that for every one molecule that I have of this, there are 12 carbon atoms. So I start with my given information, 619 grams. I have to find my moles first, then I can find a particular number of atoms. So initial mass, 619 grams. I calculate my molar mass by simply adding up all of the masses of the atoms I have present. 12 times 12.01 for carbon, plus 22 times 1.01 for hydrogen, plus 11 times 16 for oxygen. Added up, that is where this number came from. So as I said, if I have 1 mole of sugar, then I have 12 moles of carbon because that is what the subscript is. So this allows me to get to moles of carbon. The last thing I have to do then is get to atoms of carbon, which means that I am using Avogadro's number. Mole is here, so mole has to be down here. I multiply by Avogadro's number, and I see that the units that I'm left with are what I'm interested in. You have to follow the units. The numbers will continue to change. So I multiply 619 times 1 times 12 times 6.022 times 10 to the 23rd. And then I divide by parentheses 342.34 times 1 end parentheses. I end up with 1.31 times 10 to the 25 atoms of carbon are present if I have 619 grams of sugar. So you want to make sure that you are paying attention to your units and then labeling what each substance is as you go along. It will help you in the long run. So in the last lesson, we talked about percent composition, which is how much mass is each atom, each element contributing to the overall mass of a particular compound or molecule. So if we're given the percent composition, we can find empirical formula and then the molecular formula. So I'm going to take my mass percents, whatever they might be. If I have 50% of something, I'm going to assume that I have 100 grams to start with so that my percentages just become grams. So if I have 50%, I have 50 grams. If I have 29%, I have 29 grams. 71%, I have 71 grams of whatever I'm interested in. So I need to find moles. Why? Because empirical formulas are your simplest whole number ratio for a given compound. So grams to moles means that I divide by the molar mass. So I find the number of moles of each of my element in my percent composition. Then I look for the smallest number and divide it into all of the other numbers, right? This is how I simplify. This is how I get to my smallest whole number ratio. So I should come out with whole values. Whatever numbers I get here, then I just change to subscripts and then write out my empirical formula. Now, when you do this math, if you get a number that's 1.999, we can round that to 2. Or if it was 3.001, we can round that to 3. However, if you get a number like 1.25, we cannot simply just round that to 1. Instead, we would have to multiply everything through by 4. If we got a value like 2.667, well, then we would multiply everything through by 6 to get back to a whole number value. If you got a number like 1.20, we would multiply by 5. So we have to get to whole number values. You can round within reason. So a 0.998, 0.997, you can round up. A 0.0102, you can round down, and that's acceptable. So how do we apply this? The percent composition of the compound equilin is 80.56% carbon, 7.51% hydrogen, and 11.92% oxygen. The molar mass is around 268 grams per mole. What is the empirical formula and molecular formula of equilin? So the first thing that we do is we assume that we have 100 grams of this substance. Oops. So that we can say that if I have 100 grams, then that means I have 80.56 grams of carbon, 7.51 grams of hydrogen, 11.92 grams of oxygen. You can assume any starting mass, but I like to keep things simple. So if we assume 100, we can simply just change our percentages to grams. So the first step then that we take is converting into moles. I look at my periodic table to figure out what my molar masses are, and I divide by the molar mass. So grams of carbon divided by 12.01, that's the molar mass, gives me 6.708 moles of carbon. The molar mass of hydrogen is 1.01. So I divide 7.51 by 1.01. That gives me 7.44 moles of hydrogen. And we pay attention to our sig figs. We have 11.92 grams of oxygen divided by the molar mass of oxygen, which is 16.00. That gives us 0.7450 moles of oxygen. So I found my moles of my individual elements. Now I look for my smallest number. Here's my smallest number, so I divide that into each of my other values. So 6.708 divided by 0.7450 gives me 9.000 moles of carbon. 7.44 moles of hydrogen divided by 0.7450 equals 10.0 moles of hydrogen. And then any number divided by itself is 1, so I have 1.000 moles of oxygen. So you will always have one of your values come out exactly equal to 1 because you're choosing one of those numbers that will be then divided into itself. So now I take my numbers and I turn them into subscripts. So I have C9, H10, O. This is my empirical formula, simplest whole number ratios. I can calculate what is the empirical formula mass for this particular substance. Once again, I would go 9 times 12.01, because that's the mass of carbon, plus 10 times 1.01, that's the mass of hydrogen, plus 16. I only have one of these. I add them all up and I get this value. Now, to find my molecular formula, I'm going to divide my empirical formula mass into my given molecular formula mass, my molar mass of this particular compound. So 268 grams per mole divided by 134.19 grams per mole equals 2.00. So now I take that number and I multiply through my empirical formula value to get my actual compound. So it's C18H20O2. My true formula mass, or molecular formula mass then, is 268.38 grams per mole. So once you get this value, once again, you just multiply through each of these subscripts by whatever your ratio is of the molar mass of your compound compared to the molar mass of the empirical formula compound. So there's one other way that we can determine empirical formulas, and that's through experimentation, which is called combustion analysis. So remember, combustion means that we're going to burn something, and we always are burning something in the presence of oxygen. So that's how we recognize a combustion reaction. So with this, we don't know how the atoms are bonded together, and unless we know ahead of time what the molecular mass is, we wouldn't necessarily be able to figure out what the true compound formula is. But here we have an example. We have ethanol. We're going to burn it. Here is a substance that absorbs water. Here is a substance that absorbs carbon dioxide. So what we would do is measure the mass before and after so that we could figure out if we burned 11.5 grams of ethanol, you end up with 22.0 grams of carbon dioxide and 13.5 grams of water. We would then be able to use this information to determine the empirical formula with the knowledge ahead of time that ethanol only contains carbon, hydrogen, and oxygen. So the steps that we take to do this, step 1, we look at our grams of carbon dioxide to find how many moles of carbon we have, because the only place that the carbon can come out from where it started from is within the carbon, or is within carbon dioxide. So the grams of CO2 that we get, we convert to moles of CO2, and then we convert to moles of carbon. I'll talk about this step here in a minute. So we get our moles of carbon, right? Because to get empirical formulas, we need to know moles of substances. We do the same thing for hydrogen, because the hydrogen that's present in our initial compound will only come out in water. So we have grams of water converted to moles of water to get to our moles of hydrogen. Now, in step 3, how do we know how much oxygen we have? Because the oxygen comes out in both carbon dioxide and water. Well, that's where this step here comes into play. So once I know my moles of carbon, I can multiply by the molar mass to get to grams of carbon. Once I know my moles of hydrogen, I multiply by the molar mass of hydrogen to get to grams of hydrogen. If I take those two values and subtract them from my initial sample mass, then I know how many grams of oxygen were in my original sample. So not part of the oxygen that we burned, but what actually came from our compound. We keep in mind that we're allowed to do this because the law of conservation of mass always exists in chemical reactions. So once I know my grams of oxygen, I can calculate my moles of oxygen. So then I've got moles of C, moles of H, moles of O. And then it's just like empirical formula determination from a percent composition, which means we divide by the smallest number, right? We divide by the smallest number to get to the subscript. What is our molar ratio? So an example of this. Ascorbic acid, which is also known as vitamin C, contains carbon, hydrogen, and oxygen. Combustion analysis of 5.24 grams of ascorbic acid produces 7.86 grams of CO2 and 2.14 grams of water. What is the empirical formula and molecular formula of vitamin C if the molar mass is about 176 grams per mole? So we start with finding carbon. We start with how many grams of carbon dioxide do we have? 7.86. We have to get to moles. So in 1 mole of carbon dioxide, the molar mass is 44.01 grams, which comes from adding the mass of carbon, 12.01, plus 2 times the mass of oxygen, which is 16. So 12.01 plus 32 gives us 44.01. Then we recognize that for every mole of carbon dioxide that we have 1 mole of carbon that comes from the subscript. So we do our conversions, we multiply everything together on the top, we multiply everything together on the bottom, and then we divide. Sig figs, 3 in the front, 3 in the back, 0.179 moles of carbon. Now I look at my mass of water to find how many moles of hydrogen. 2.14 grams of water. My molar mass of water is 18.02 grams per mole because I have 2 times 1.01 plus 16. So that's where the 18.02 comes from. Grams cancels with grams. There should be a cross here too. The moles of water will cancel with the moles of water. Now this is the tricky part, or the thing that we tend to forget. For every mole of water, we actually have 2 moles of hydrogen. So here it's a 1-to-1 conversion. Here it's a 2-to-1 conversion. But we multiply everything through on the top. We multiply everything through on the bottom. We divide the bottom into the top. We get 0.238 moles of H. So now we have to figure out how many grams of oxygen we actually have. So I'm going to take these moles that I just calculated and go back and find, well, what is the mass of this particular element then? So I use the molar mass of carbon. I multiply by the number of moles I have to cancel those out. So 0.179 moles of carbon equals 2.15 grams of carbon. I do the same thing with hydrogen. 0.238 moles of hydrogen. I multiply by the molar mass. That gives me 0.240 grams. Now notice over here, we're not using 2 moles. This is just the molar mass of what 1 hydrogen weighs. So the only place we use that 2 mole H is over here in determining our initial value of moles of hydrogen. So now I have my grams of carbon and grams of hydrogen. I add those together. I subtract them from my original sample mass, right? 5.24 grams. So I subtract that. And then I find that I have 2.85 grams of oxygen in my original sample. So now I have to find moles of oxygen. Once again, if I have grams, I need to get to moles. I divide by a molar mass. I look at the periodic table, see that the molar mass of oxygen is 16.00 grams per mole. So 2.85 divided by 16.00 gives me 0.178 moles. So I found my number of moles. Now I look for my smallest number out of these three and see that it is 0.178. So I divide that into each of my other substances and my oxygen. So this into this, right, gives me 1.00 moles of carbon. This into this gives me 1.33 moles of hydrogen. And this into this gives me 1.00 moles of oxygen. Oh, that's a typo there. That should read 0.178, my bad. So what do I do here? Well, why do I have this times 3? Because my moles of hydrogen are 1.33 moles. This is not a number I can round down easily. That's not allowed. I cannot just round that to 1. But if I multiply this by 3, I see that I get close to a whole number value of 3.99. That we can round up. So what I do to one thing, I have to do to every other thing. Multiply each of my moles through by 3. So then I have 3 moles of carbon, 4 moles of hydrogen, and 3 moles of oxygen. I take those moles and I turn them into subscripts. C3H4O3. This is my empirical formula. I can find the molar mass of this substance by going 3 times 12.01 plus 4 times 1.01 plus 3 times 16.00. That is where this value came from. To determine what my molecular mass is, or my molecular formula, I take the given molar mass of 176 grams per mole. I divide that by my empirical formula molar mass and see that this ratio is 2. I multiply each of my numbers, each of my subscripts here by 2, and I get to the true molecular formula for ascorbic acid, which is C6H8O6. Determining that molar mass is 176.14, so we are very close then to what our initial value was that was given. I know in the previous problem where I did a percent composition to empirical formula to molecular formula, our ratio came out to be 2 there as well. That's not always going to be the case. Sometimes it's 1. Sometimes your empirical formula is your molecular formula. Sometimes it might be 3 or 4 or 5 or 6. It just depends on that particular substance's empirical formula and then what the molar mass is of the molecular formula.